let's go over this problem from discussion. So this is a problem that will start as a static equilibrium problem for part A, and then in part B we're going to sort of cut the string here, and it'll be something that's going to be angularly accelerating. But let's look at part A first. So a uniform meter stick of mass 1.5 kilograms is attached to the wall by a frictionless hinge at one end. So there's a hinge on the one end over there. On the opposite end is supported by a vertical massless string such that the stick makes an angle of 40 degrees with the horizontal. So again, it's always good, I think, to work through these together. So why don't you take a second here and try to figure out this question, which could be a quiz style question or exam. What is the tension in the string? So again, start out, write out your free body diagram and then use our equations for static equilibrium to see what you can do there. Okay, so hopefully you did that, and when I did that, I got the answer of 7.35. And so let's go through and do this. So for my free body diagram on this meter stick, there's the tension in the string over here. There's going to be mg, the mass of the stick, and that's going to be right there at its center. Now over here there's a hinge, so this is always a little bit weird, but in general I think unless the problem is really clear, we sort of assume that these hinges and stuff could be applying an X force as well as some kind of a Y force. Again, occasionally you'll have something like they'll tell you that there's no friction there or something, or they'll give you some hint that there doesn't need to be, but I think just to be safe it's always good to write out those forces. And so this is our situation now, our four forces. And so again, if this was a quiz question to find the tension, I would argue that the best place to make our axis is right over here, right at the hinge. And in fact, in this case, we can start that way and find the tension pretty nicely. And so let's go through and do that. One more adjustment I'll make is that, so in the problem, we're going to sort of call this here, this is our angle theta, which was again 40 degrees. And so what I'll do is our sort of typical thing here. I'll just jump right into the positive torques equal the negative torques. And so if that's our axis, then in my calculation the tension will be doing the positive torque, and then the mg will be doing the negative torque. And so the trick here is to find our distance for this torque, and so our moment arm. And so if you look here, so the way we do this is, like for instance with the tension, we draw the line of action, this imaginary line through the force, and then what I'm going to do is I'm going to find this distance here, which is the shortest distance between the axis and this line of action. Another way to think about it is it's sort of the component of the ruler stick's length that's perpendicular to the tension. That's what's going to give us our moment arm. And so in this case here, if I write that out, and it looks like I didn't give myself quite enough room, let's maybe I'll write it over here, but that would be tension, and then that red part there would be tension cosine theta. So I'll just sort of write it like this. Tension, so it's tension, and then it's going to be the length of the stick times cosine theta. Now it's a meter stick, that'll end up being 1 meter, but either way, that's that little distance right over there that I covered in red. So again, this is t cosine theta. Now similarly, to find the other one, I'll go ahead and use blue. And so the same sort of idea. I'm going to draw this imaginary line through the mg, and in this case it's just going to be, it's basically the same distance, just half of it. And so it's just this distance right over here would be the moment arm for that guy, and so that would end up being L divided by 2 cosine theta would be that one there. And so we write this into our equation, L divided by 2 cosine theta. And so what's nice here is that sort of the cosine thetas cancel, and then the L's cancel. It just makes our life a little bit easier. And so when we're all done, we get T equals mg divided by 2, and so that's 1.5 kilograms times 9.81 meters per second squared divided by 2, and when I did that I got the 7.35 newtons. Okay, and so that is something that could have been a quiz question. Now what in this problem we then want to find out the force from the hinge. So again, like we do with these kind of problems typically, so we use, oftentimes you can use the torque equation to do sort of the first part, and then in the second part, kind of figure out everything else from our force equation. So the torque is what we use initially. So here's again this tension, this mg, and then just to be safe, I just assumed that there's two forces here. And again, these are the kind of things, so I'm guessing that it points up and it points to the right. It could be the opposite of that. And so you can sit there and think about it and reason through if you want, but you can also just guess. And then when you do your equations, you'll get like an answer that's negative if you guessed wrong. And so here I'll start off with the sum of the forces in the x direction, which basically if I look in the x direction, the only force I have is that f of x. And so if I go through and add it up, again, I'll use my sort of typical xy axis here. That's the only force from this side. That equals 0. So we see right away that there is going to be no fx force. So we put it in there, we didn't know, but because there's no other forces acting in the x direction, this wasn't needed. There's no other force sort of pushing that meter stick into the wall or pulling it out, and so that hinge doesn't need to sort of have a force that way. And then if I sum up the forces in the y direction, so again I'll have a positive Fy, a positive tension, and then negative mg. And if we sort of write that out like this, then kind of what I'm saying is Fy plus the tension equals mg. And so we can see here that Fy will equal mg minus the tension. And if we remember the tension in our last page, it was just mg divided by 2. So mg minus mg divided by 2 comes out to be mg divided by 2, and this will equal, again, the 7.35 newtons. Now, what's going on here is this will happen in cases like this where, so there's our two x forces, and they're all the way on the end, and the mg is right in the middle. And so basically, because of that sort of setup, they're going to end up each holding half. Now, you could change these problems to have that sort of tension come at some different point on the stick, but in this case here, this is how it works out. So part A, sort of a standard static equilibrium question. Now let's move to part B. And so part B is now we're going to cut that string, and we want to find the initial angular acceleration. And so the way we're going to go about doing this is to say the sum of the torques equals I times alpha. So why don't you just stop for a second, sort of think through this and see if you can get an idea, and we'll come back and we'll talk about it in a second here. Okay, and so we're going to go through and figure out the forces or the torques on this, and then use our rotational version of Newton's second law. And so if we look at the forces here, again, this string is cut, so there's no tension there. There's still the mg of the stick. And then over here, so we'll just sort of say that there is a force Fy over here at that moment. Now, in this case, when we cut that string, we can see that it's going to rotate about this point. And so this is going to be the point that we want to make our rotational axis. All right. And so what I'm going to go through then is figure out my torques. And again, over here, my torque in this case would be mg L divided by 2 cosine theta. So this is the same torque we found just a little bit ago, right? And it's the same sort of idea. If I draw my line of action through here, then this distance is our moment arm. And again, this sort of little distance right here would be L divided by 2. And this, again, is our angle, which is 40 degrees starting out. And so this side would be L divided by 2 cosine of that angle, just like that. So when I express the torque, I'll get, again, the force, which is mg, and then the moment arm, L divided by 2 times cosine. Now, if we look up online or in our book, we can find that the moment of inertia for a rod about its end is 1/3 ml squared, where L is the length of the stick, m is the mass, and then 1/3 is this sort of front factor. And again, this is for a case for some long stick, like our case here, going about an end or rotating about its end, which again is the picture that we have. So I'm going to put 1/3 ml squared over here, and then we have our alpha. And what is it that we're trying to find here? We're trying to find our alpha. And so I can set that up, and so our alpha will end up being the torque mg L divided by 2 cosine theta, and then dividing by 1/3 ml squared. And so if we end up looking at this when it's all said and done, I got 3/2 g divided by L cosine theta. And let's go ahead and plug in our numbers to that. All right, so when I plugged in the numbers again, the key one is that this angle is 40 degrees. I got 11.26 radians per second squared. So it's an angular acceleration. Now, technically, we could go back here. Usually with a question like this, we're thinking more about the magnitude. But this technically would have been a negative torque, which would have made this negative and this thing. And so technically, it's a negative torque. But again, in a case like this, we're generally looking for the magnitude of it. So hope this helps. Thank you.